for setting up the workshop and for giving me the opportunity to talk here. I'm going to tell you about the work that we have been doing in the recent few years. It's basically a research program. We have gone through it so far, and hopefully we'll continue it in near future. That concerns the symmetries at null boundaries. Basically, the main question the main motivation for studying this is basically coming from black holes. But you can ask the same question in a more general setup. Whenever you have a gauge theory, including gravity, and you want to formulate this theory in a part of the space-time which has a boundary, and this boundary could be a real physical boundary or some arbitrary surface in your space-time, what do we need to do? So that's basically the kind of question that comes up in black hole physics when you want to formulate physics of or dynamics around the black hole if you are an observer outside the horizon, outside the black hole. So, and from the viewpoint of this kind of observers, those observers who are fiducial observers not falling into the black hole, the horizon actually appears as a null surface, which is the boundary of the space-time this set of observers are finding in. And the question is, what happens if you want to formulate gravity in this setup? Okay, so, but the general setting is gauge theories in presence of boundary. Okay. So this is the outline of my talk. I'll basically review the fact that if we want to formulate Einstein gravity in presence of boundaries, we need to basically revisit equivalence principle and allow for the so-called boundary degrees of freedom. And in particular, for the case of black holes, it would be of interest to focus on null surfaces as boundaries, which are models for black hole horizon, and then try to formulate this general problem that I just mentioned for this null boundary. And as we'll review, for the null boundary, we construct the most general solution space for theory of Einstein gravity. And as we'll discuss, there are d number of functions on this null boundary, which parameterizes the solution phase space. And we'll basically try to study this solution phase space, and we come up with the null boundary algebras, which are the symmetries on this solution space, and then we go on with defining charges associated with these symmetries. This is basically an extension of Noether theorem, and I'll summarize with an outlook and how this could be relevant to the question of black holes in the end. Of course, I don't have the full answer to the main question we are asking, but I'll basically try to give you an outlook. So let me start with considering a gauge theory. So let's suppose that we have the, can you see my pointer? Okay, so
yes, we can see it, yes.
Okay, thank you. So let's suppose that we start with a gauge theory action, which is basically described by this D-form Lagrangian, defined on a manifold M. And let's suppose that this is a gauge theory, meaning that these fields are defined up to representations of a given algebra, and these are representations. And the gauge invariance means that these two actions for phi tilde and phi are equivalent. And as we all know, in gauge theories, and degrees of freedom or physical observables are defined up to gauge equivalence classes, and gauge symmetries are viewed as redundancies of description, and we fix or remove these redundancies by gauge fixing. But the point is, so this is the general practice that everybody's familiar with, but there could be some interesting subtleties when we have a boundary in space-time. And one can ask whether the gauge transformations, how do they act at the boundaries in particular, and whether the configurations which are not equivalent up to these values of fields at the boundary are physically distinct. So basically, let's suppose that we just do the usual thing. We study the variational principle, which gives us the equations of motion and a boundary term, and the boundary term, vanishing of the boundary term is basically giving us the appropriate boundary conditions. In my talk, I'll not be concerned with whether really this boundary term is going to vanish or not. This is an interesting question that one can ask separately. So instead, what I'm going to allow is basically to allow for the fields and their variations at the boundary to have some non-trivial values, and they can take different values at the boundary. And they are not in particular gauge invariant or not necessarily invariant, no, I mean compatible with the kind of gauge fixing that we have used. Okay, so in particular, there could still be some measure zero subset of gauge transformations under which this boundary values of the fields transform. And the question is whether this could be, I mean, studied in a more systematic way. And basically the question is, how do we specify this set of measure zero subset of gauge transformations which change our boundary value of the fields? As we'll see, one can associate some conserved charges to these specific variations, gauge variations, and hence can treat them as something physical. Okay, so here I'm going to advocate this viewpoint that there are boundary degrees of freedom wherever we have boundaries, and these boundary degrees of freedom could be labeled by the boundary gauge transformations. And in particular, there is a maximal boundary phase space, which is regardless of, I mean, if we relax all possible boundary conditions, we will remain with this boundary phase space. And these are new degrees of freedom which are confined to live at the boundary, and they are not propagating to the bulk, but they do interact and with what we have in the bulk and among themselves also. And so let me give you an example here to basically clarify what I'm calling boundary degrees of freedom is not something which we are not familiar with. Let's suppose that you want to, for example, formulate a Maxwell theory inside a perfectly conducting box. So what we usually do is basically, we know that there are surface currents and there are some degrees of freedom which are residing at the boundary. And typically we, for example, know what is the physics of the boundary, for example, the perfect conductor. And those degrees of freedom are coming from this fact that we know what the boundary is made of. But if I don't want to know what the boundary is made of, or the boundary in specific cases that are of my interest is not a physical boundary, then I can ask whether gauge invariance could be used to label these boundary degrees of freedom. So basically, the boundary degrees of freedom, as I'm trying to formulate them, is basically a sort of macroscopic or hydrodynamic description of what we may have in this example of perfectly conducting plates. And basically, studying the gauge invariance and how it precisely acts at the boundary gives me a way to label and formulate this boundary degrees of freedom without delving into the details of what the boundary is made of. This is why actually this approach is hopefully useful for formulating the questions regarding black holes. So,
sorry, I have a question.
Please,
Yeah.
please.
Yes. So is it expected that the boundary conditions are uniquely fixed by the by some physics conditions, or are they not unique?
Okay, so that's a good question. Here in this talk, I'm taking the viewpoint that I'm allowing for all possible boundary variations. But you're right. Usually in physical systems, like the example that I gave, Maxwell theory in perfectly conducting box, the boundary conditions are actually given to you, prescribed by the setup of the problem.
Okay, thank you.
But here I'm taking a more sort of free viewpoint on the boundary conditions and allow all possible variations at the boundary. But you're right. In a full physical setup, we need to specify the boundary conditions in order to specify the problem completely. Okay, so let me now turn to Einstein gravity. As we know, this is based on equivalence principle, and basically equivalence principle in our formulations appears through diffeomorphism invariance, which could be viewed as some local invariance of the theory, namely if we change the coordinates with this general diffeomorphism, the metric, which is the dynamical degree of freedom, changes in the standard way with the lead derivative of the metric along this diffeomorphism. And basically, the action remains invariant under this transformation. And the question now is, what happens if we want to study the same problem and diffeomorphism invariance of the theory in presence of a boundary? Actually, the fact that we may have some boundary degrees of freedom, which means that there are some subset of these diffeomorphisms, which takes us from a physically distinct solution to another physically distinct configuration, means that there's this measure zero subset of these diffeomorphisms, which do not act at the boundary, is going to be non-trivial. And this means that I need to amend the equivalence principle, considering the existence of this non-trivial diffeomorphisms. I'll go through this in more specifically in this setup of the null boundary case. Okay. Let me review what we have for d-dimensional gravity. In d dimensions, we have some number of metric components, d times d plus 1 over 2. There are d times d minus 3 over 2 of these, which are propagating gravitons. And then there are d number of components which could be fixed through diffeomorphism. So this is the standard practice. Among the equations of motion, again, we have the same number of equations of motion, out of which the same number as the propagating gravitons are second-order differential equations in time. And then there are the number of constraints. These are first order or zeroth order in time derivative. So, so this is the setup of the problem. And the point is, once we fix these diffeomorphisms, we remain with the number of functions which are specified on codimension 1 surfaces. And we need to specify this to fully specify the solution. And basically, these are, you can think of these d number of functions over codimension 1 surfaces as our Cauchy data that we need to specify to fully give you the solution. Okay, and okay, so basically, this is what we are already very familiar with. If you view these equations as some Cauchy value problem. So, but let me now turn to the question of black holes, and where we have null boundaries, and try to go through basically the ideas that I just reviewed for you in this specific example. So as I just discussed, I'm going to take these null surfaces H plus and H minus as my boundary, and I'm interested in basically formulating the physics from the observers who are sitting in this region 1, in this pink region, and basically, to formulate this problem, I take my coordinates in this specific way. I take this r equal to 0 to be a null surface, and basically parameterize the other two coordinates with v and xi. I is running from 1 to d minus 2. And this is the most general kind of metric that I can write, and has r equal to 0 as a null surface, provided that this relation is holding among these functions in the metric. Okay, so as you can see, there are I can basically decompose this in terms of tensors and vectors of this d minus 2 dimensional part. Okay, so basically this is another view of the more general setup. We have this sigma, which is the red line, which is a null surface parameterized by v and xi, which are basically transfers to this plane. This surface is r equal to 0. Inside and outside is basically where r is negative and positive. We could have infalling null rays, which are, for example, flux of graviton, either way, falling in or coming out of this null surface. Now, basically, I want to formulate the theory with respect to this boundary, and basically specify what are the boundary degrees of freedom I need to add to the problem if I want to formulate the physics only in r bigger than 0 region. So if I want to ignore what is going on in this negative r region, I can do this, but I need to add some boundary degrees of freedom and allow this boundary degrees of freedom to have their own dynamics. So that's basically the kind of problem I'm going to formulate. Okay, so let's start with trying to analyze the equations of motion. So as I just mentioned, we have two scalars, one vector and one tensor in the metric that I just decomposed in this way. But then actually this d minus 2 dimensional metric, we can take out its determinant, which is a scalar, and add it here, and then basically keep the determinant free or traceless part of the transverse metric. Okay, so these are all functions over the full space-time, and they are subject to Einstein field equations. A careful analysis of the Einstein field equations tells me what the solutions are and how they are parameterized. and this is the outcome of a very detailed analysis. I just skip the analysis and tell you the result. So Einstein equations basically tell me that these solutions in the most general case are specified by two tensor modes, which are basically the value of the traceless part of the transverse metric at r equal to 0 and its derivative with respect to r, again at r equal to 0. The vector part is specified completely by the value of the vector at r equal to 0. And the scalars basically are specified through two scalars and the scalar part. So all in all, what I remain with as my solution space, they are specified by two tensors, one vector and two scalars. These are all functions of v and xi. Okay, so I have two scalars, one vector and two tensor modes as a function over the null surface. Okay, so this is the summary. This is basically once I specify these, which are functions over this null surface, I have specified the full solution. So this is what comes out of a detailed discussion on the equations of motion. The only thing I have used in this argument is the smoothness of the metric at r equal to 0 and nothing else. In particular, I have not imposed any specific falloff behavior or boundary condition around r equal to 0, which is my boundary. And okay, so this is hence what I call maximal solution space. And any solution to Einstein equations should be specified, should be basically within, fully specified within the giving these functions, basically. Okay, now I have my full solution space. Again, I have the usual gravitons, one vector and two scalars. These are basically the boundary degrees of freedom, as we'll see. There are d number of them. And okay, now that we have the solution space, you can ask whether we have symmetries on this and whether there are transformations which takes one of these solutions to another solution. And the answer is yes. Actually, consider this specific diffeomorphisms around r equal to 0. So as you can see, these diffeomorphisms are carefully chosen such that r equal to 0 remains r equal to 0. These the t and yi parts being a shift in v and a shift in xi are clearly not changing r equal to 0, and then this w part is scaling r, so it keeps r equal to 0 as it was. So basically, when I act on one of these solutions in my solution space by this specific diffeomorphism, I'm out to basically I need to get this another solution in the same space, because I told you that I have fully specified all the solutions at r equal to 0. In particular, if you act by these diffeomorphisms, you can see that very explicitly. If I appropriately change this boundary plus bulk graviton nodes, which basically keeps me in the same solution space, these diffeomorphisms takes me from one solution to another. Okay, so these are hence symmetries in the standard sense of Noether. It takes one solution to another. So you can ask whether we can associate conserved charges to these symmetries. But before coming to this question, let me summarize here. We have d times d minus 3 propagating tensors, which are the bulk modes. These are modes which are propagating in the bulk, and the scalar and vector modes, specifically 2 scalars and 1 vector mode, which are only residing at the boundary. These are the boundary modes. Okay. In order to come to the question of charges, basically, there's a well-defined procedure. That's the solution phase space, and is basically building up upon the fact that the solution space is endowed with a symplectic structure and is hence a phase space. Okay, and basically let me come to this. Basically, sorry, let me move on. There is a very well-defined way to construct the symplectic structure given a Lagrange. I'll just, if you want, I can discuss it after the seminar, but there is a very well-defined procedure, which basically defines for me the symplectic structure on a given solution space and makes it a solution phase space. Using the same machinery, I can actually define conserved charges associated with each and every symmetry transformation that I have. And the end result is that there are charge variations associated with each and every symmetry generator that I've denoted by chi. And these are given by the surface integrals over codimension 2 surfaces of over some function that I know in principle how to construct for a given theory. So that's basically the bottom line. This is basically a charge variation over the solution phase space. And the question is whether this charge variation is integrable. And if it is integrable over the solution space, which means that this is delta of something over the solution space, then I can define the charge itself based on this charge variation. Okay, so this is the general picture, and this allows me to associate conserved charges to the symmetry generators. But let me now actually tell you more about this algebra of the symmetry generators. I basically gave you this diffeomorphism specified by 2 scalars, t and w, and a vector yi, and you can basically study the lead bracket of these diffeomorphisms, as I've done here, and it's not a surprise that this lead bracket closes on the same set of diffeomorphisms with this specified specific algebra. And so this is basically the null boundary symmetry algebra, which is diffeomorphisms on a cylinder. The cylinder is basically parameterized by v and xi, and the y transformation, which was the scaling in the r direction, as you remember. So this is basically the symmetry algebra that I have. This is the symmetry for this is the algebra for the symmetry generators. These vectors, diffeomorphisms, and there is a fundamental theorem of this covariant phase space method, which tells me that the same algebra is obeyed by the charges associated with these diffeomorphisms. Okay, possibly there could be some central terms, but the algebra of charges is the same as the algebra of generators. This bracket here is the Poisson bracket over the phase space, the solution phase space. Okay. Now I have the full machinery in principle, and I can basically apply this to my own problem. That's basically Einstein gravity with this null boundary and this set of symmetry generators that I just discussed. Doing so, we'll get this charge variations, which are integrals over the constant v slice over the null surface that I had. So this is an integral over the xi part of the geometry. You can think of this for example, in the Schwarzschild case, this part is the sphere. For the black hole case, these are typically bifurcation surfaces or the codimension two horizons. Anyway, the charge variation is an integral over a codimension two surface, and this is the expression. As you can see, this is linear in the symmetry generators W, Y, I, and T, and it's multiplied by some functions over the phase space, variations of some functions. But as you can see, actually, the charge is not integrable in the sense that this delta slash of A is some function made out of the functions that I have in my solution phase space, is not variation of anything on the phase space. So it's not a closed one form over the solution space. This means that this cannot be written as delta of something over the solution space. So the charge is not integrable. And to be more precise, the charge associated with W and Yi, namely the omega. Remember, omega was the square root of the determinant of the metric at the horizon. So this is sort of like the entropy of the black hole, if you wish. This is the angular momentum. And this part is not integrable, though. Okay. So this is basically what I just discussed. Since there's a non-integrable part in the charges, one may ask whether we can basically separate this charge variation into an integrable part and something different left over, which I've called flux. And whether there's a unique way to do this decomposition, the answer is yes. And this is a method due to Barnish and Trossard. About 10 years ago, they introduced this method. And it's basically saying that if we have the integrable of the part of the charge, it should obey the same algebra as the symmetry generators. So basically, requiring this gives us a way to decompose almost uniquely the charge variation into an integrable part and a flux. So this is basically trying to require or impose the basic theorem of solution phase space or covariant phase space method, namely this equation, that the algebra of charges should be the same as the charge of the bracket, the symmetry generators. And hence the symmetry algebra of the charges, the integrable part of the charges, is the same as what I had before for the symmetry generators. I have written this very explicitly. As you can see, I have two scalar type charges and a vector type charge. Okay. And this theta is the expansion, the standard notion that we have. So if you have any surface, you can define the expansion. This theta is the expansion for this null surface, and omega is basically the volume over the constant V slice. For W equals to 1, this is nothing but the Bekenstein-Hawking entropy. And for constant Yi, these are nothing but the standard angular momentum, for example, if you started with a Kerr solution. So this is basically the same algebra that I told you. And there's a flux, which is proportional to T, as we discussed. That's the non-integrable part. As you can see, actually, the flux involves two different type of terms. One is the part which is basically not involving the gravitons, and a part which is proportional to the graviton. This Nij is proportional to the bulk modes. Okay, so even in the absence of the bulk modes, the charge is not integrable, which is interesting on its own. But I'll come to this fact shortly. But before that, let me discuss a bit the dynamics of these charges. These charges are not actually conserved in the sense that they are V dependent. I'm viewing this V as the time over the null surface. If you are an observer who is living at the boundary, basically you have a d-1 dimensional theory on this null surface, and V is basically your time coordinate. The time derivative of these charges is exactly equal to the part of flux along this V direction. This is in the standard gravity case, and if you took the boundary to be the null infinity, this is called the balance equation, or the Bondi-News actually is this what this flux is. But our setup is more general. The null surface is is an arbitrary null surface in anywhere in the space-time. So we have this more general balance equation. And you can view this basically as what remains of the Einstein's equations, but written in terms of these charges. Okay. These charges actually allows me to define what I call null surface thermodynamics, which actually for specific cases reproduces the first law for black hole thermodynamics. So this is a much more general setup in this sense than standard derivations for the black hole thermodynamical laws. So in view of time, actually, I skipped through the details of this, but we have this kind of zero mode charges, which are behaving like entropy, angular momentum, and energy, if you wish. And the entropy is commuting with all the charges as is what is needed if we want to label so-called black hole microstates by these charges. They should commute with the entropy. And more interestingly, we have a relation among these charges. This is a local equation at each and every point on this null surface among these charges. This is basically something like, you can view it as a first law or something like a smart relation. So that's basically how Einstein equations manifests itself in this setup. There's an interesting case which is related to usual black holes that we are familiar with. And that's basically when the expansion is zero. This is sort of what we have for the case of stationary black holes, and when this null surface is the horizon. In this case, actually, one of the symmetry generators, in particular this T, becomes a pure gauge, and we can fix that gauge and remain with one scalar and one vector charge. Let me skip this part in view of time and basically try to summarize and tell you how this could be relevant in the end to the question of microstates of black holes. I already told you the hints that I have here. So first, I discussed that the presence of boundaries introduces new boundary degrees of freedom on top of what we have in the bulk, for example, the bulk gravitons. And that these boundary degrees of freedom are classified and labeled by non-trivial diffeomorphisms. And so my basically degrees of freedom, my full solution space, if you wish, are now involving boundary plus bulk degrees of freedom. And these are coupled to each other. The boundary degrees of freedom interact among themselves and interact with the bulk through Einstein equations. And basically, these are sourced also by the gravitons in the bulk. So to be specific, basically physics out of the horizon in our bigger than zero region as I just showed in that figure, is described by boundary plus bulk degrees of freedom. So I can cut out the negative R region, but I need to add these boundary degrees of freedom to the system. And that's basically what one should do if you want to, if you are an outside observer and you want to formulate physics physics out of the horizon in the outside region. And these boundary degrees of freedom are, as I just mentioned, and the setup suggests, could be somehow related to possibly to the black hole microstates. And I just discussed that in the algebra of these charges or the symmetry generators, which moves me on the boundary phase space part, is basically labeled by the d-1 dimensional diffeomorphisms and while scaling. In some change of slicing on the phase space, it could be brought into Heisenberg algebra plus diffeomorphisms on the codimension 2 surface. So that I skipped this part, but this is a bit technical. And in the next 2 talks of this workshop, you can basically hear more about these details. So this is why I skipped through this, because there are the next 2 talks. And basically what Einstein equations tells me is that there are boundary degrees of freedom which interact with the bulk degrees of freedom through the bond in use. And the balance equations are basically, which are manifestations of Einstein field equations from the viewpoint of the boundary observer, is telling me how the boundary degrees of freedom are interacting or sourced by the bulk modes. The formulation that I just set up here is good enough to give me a way to formulate the so-called memory effect, and in particular, the memory effect at the horizon. So the boundary degrees of freedom, the degrees of freedom which are residing at the horizon, are basically a bookkeeping function or bookkeeping method to know, to let us know what has passed through the horizon to the r less than 0 region. In this sense, this is basically a memory effect. So far, what I told you was classical. One can quantize this basically by replacing, we have a solution phase space, we can replace Poisson brackets with commutator and promote the functions over the phase space to operators, so the standard quantization procedure. And in particular, we need to quantize boundary degrees of freedom. And the idea is that that quantized boundary degrees of freedom are eventually going to show up as black hole microstates. This last part is basically very close to the idea that Hawking Perry-Strominger had, the soft hair proposal, but they didn't have the right setup to formulate the problem. So we think that this is what I just presented here is the right formulation. So we have everything ready to take on the software problem and try to formulate a software proposal. There are many technical issues which should still be understood, and I've listed a few of them here. And and the last thing that I want to mention is actually the way I presented this and the fact that we have some boundary degrees of freedom and that boundary degrees of freedom are residing at the null surface is very closely related to the membrane paradigm picture. And hopefully the software proposal, this basically gives us a way to more precisely connect the membrane paradigm to the software proposal. So let me leave you with this last slide, and thank you for your attention. So I'd be happy to take questions if there are. Thank you.
Hi, Shaheen. So I have a question.
Please.
So quite some time ago, Steve Carlip was arguing that for usual four-dimensional Schwarzschild black holes, there is a Virasoro symmetry on the horizon. Is this something which you can see, or is that wrong?
Okay. No, this is a very good question. So let me go back to basically a bit of translation is needed to answer your question. Actually, in this, what Carlip had was about this R and V part of the geometry, the part that is now, you can see it here. And what actually the first version of what Carlip had was a Virasoro, but then there was some later, so that was 98, 99, that the version that you mentioned. But later on, Carlip actually extended that in 2017 and 2019. He extended that Virasoro to BMS3. Okay. Oh, but and then the argument was that this BMS3 admits some central charge, and then you can use some Cardy type formula to read the entropy. So that was the general picture. In my language, actually, if you ignore this transverse part and only focus on the V and R part, you get so these two charges, basically the charges or the symmetry generator T and W. There are two of them. We don't have these Y's because we have ignored them. And then there are two charges. Actually, upon some massaging the formulation and so on, these two charges satisfy a Heisenberg algebra. So these are two functions over this null surface. And actually, given a Heisenberg algebra, as you know, one can basically readily construct, for example, SL2R. You can just square these to get SL2R. And these are functions over the phase space, and that's nothing but the BMS3. So what we have found is extending what Carlip has. Okay, so what we have is much bigger algebra because we have this other, the vector part as well. And and actually, I need to give more words on this because many people do not take Carlip's setup and arguments for a good reason. And the intuitive reason, I mean, at the end of the day, is that if there's any black microstate, you would think that it should be residing on the sphere part, not on this R and V part. Right. And for example, there are this Kerr CFD or Strominger's BTZ black hole microstate, the famous paper of 97 and so on, is all pointing to this direction that black hole microstates should be arising not from the R and V part, but this XI part. Right. So there is some truth, some good physical point in Carlip's description, but that's not the black hole entropy or the microstate. Yeah. Okay, so this R and V part actually has more to do with the more dynamical processes. For example, things can pass through this. Or the Hawking radiation, the unitarity or information problem, and so on. So if the question of microstates is concerned, It's more like stationary thermodynamical behavior of the system. It should be related to this transverse part, but more dynamical things, having fluxes through the horizon and so on, is related to this V and R parts.
Got it. Thank you.
Sure. So, if there are any other questions or comments.
Hi, Shashi. You mentioned the horizon memory effect. So I just wonder, I mean, normally when you have the memory means some radiation cross the horizon. So can you guarantee that the horizon cannot be destroyed by the radiation?
Okay, so this is a good question. In my setup, actually, it's sort of idealized in the sense that I keep this surface to be a null surface. Maybe at some V less than something, we have the null surface, but when some flux of gravitons passes through, let me go to the next page, then this breaks up and it settles down to another null surface, right? So there's a breakage here, if you wish, if you can see my cursor. So if you ignore this very specific time that, for example, if shock wave passes through the horizon, I can, before and after that, I can use my formulation. So then the question is, what happens at the jump? And at the jump is exactly the information about the shock wave is now coming through the change in the surface charges. What we call about memory effect. So if you ignore that specific point in time that the shock wave passes through, then the rest of the system is described with the formulation that I just presented.
Okay, thank you.
Sure. I should add that we have not published this yet. So, and a part of these are still in progress. So, and I also mentioned many open problems in the end. Some of them were technical and some of them were physically very interesting. And you are very welcome to join us. Okay.